Okay, dear colleagues, let's start our seminar. And today's speaker is Shuai from Peking University. Please, you are welcome.
Okay, should we start?
Yes, we can start.
Okay, so today I will talk about the Birkhoff factorization, Givental's quantization, and the BCOV's Feynman rule. So this talk is based on joint work with Hualiang Chang, Jun Li, Weiping Li, and Yang Zhou. Okay, so the question we are considering is the so-called Gromov-Witten invariants. So we want to compute this Gromov-Witten invariants of some Calabi-Yau threefold, so X. Because when X is Calabi-Yau threefold, so the main information for the Gromov-Witten invariants is just lies in the primary Gromov-Witten invariants without insertion, meaning that we consider this so-called NG beta. Which is defined by this is 0 x beta. This is the modular space of stable map, and we can, because for Calabi-Yau, when X is Calabi-Yau, this virtual dimension is just 0, so we just consider this number, and it is clear that you can apply the so-called string equation, dialectic equation, and the divisor equation to deduce all the other Gromov-Witten invariants by this fundamental Gromov-Witten invariant. And we also introduce some notation, standard notation. So usually we will write this bracket. So here we put some like gamma 1 psi 1 k1 to gamma n psi n kn. So gamma I is just lies in the common class of X, and this is G n beta X. This is just the standard notation, and this is the integrations over the modular space X beta, and with some this is the pullback of evaluation map of gamma I and some psi class. And when we write a bracket without this beta, we means we summation over all the possibilities of beta for beta effective of this. So here Q is a formal variable called the non-equal variable, and if you consider the modular space, you can also consider this Q as a local coordinate near the origin point of the Taylor cone. So maybe I will recall this later. Okay, so usually maybe here we use the big Q because we will have some small q later. Okay, and then for when the genus is equal to 0, this problem is just solved by the classical mirror symmetry. So I will first recall the so-called mirror symmetry. So the classical mirror symmetry, or I say the genus 0 mirror symmetry. It is saying that, so you have, so here we are considering some Calabi-Yau threefold X. So to be precise, in fact, we're considering some Calabi-Yau threefold X with some Kähler class omega. And here, this Q, you can think it as something like the e to the 2 pi I of omega. Okay, so okay, maybe I should say that Q to the beta, you can think it as e to the 2 pi I of this omega integration of beta. Beta is some because here beta lies in this 2 of x, and omega is a Kähler class lies in the H upper 2. Yeah. Then the mirror symmetry say that you have a family of this Kähler Calabi-Yau threefold, and you will have some mirror family called X check. J is the compass structure, and this is called the Kähler moduli. And this is called the complex moduli. And okay, so we are considering some we considering the local structure near the large complex structure limit and the large Kähler structure limit. So which is corresponding to the big Q equal to 0, because when this omega is large, log omega somehow goes to something like this. So that's corresponding to Q equal to 0. So we have the local coordinate Q and this big Q. This local coordinate here, we call this small q here. And we usually assume that at this point, so because we can consider the considering the monodromy near this point, and we assume that for the Gromov-Witten theory, the monodromy is the so-called maximal unipotent monodromy, which means that for example, so here this is the mirror Calabi-Yau X check, and you have a holomorphic 3 from omega over 8, and this omega of course depends on this Q, so we can define the period integral defined by this omega k. It's just this. Maybe I just write it as ik. Okay, maybe let me fix some notation here. So, okay, so first this Calabi-Yau threefold, we assume that it has the dimension h is of the h2, so dimension h. This h is defined by the h2x. We assume the dimension is h. This is just h11x. And then the mirror. So the mirror symmetry first told us that this okay, because we consider the Kähler the Calabi-Yau threefold, it has symmetry, so we can write down its Hodge diamond. It looks like H1. Oh, sorry. I should say it looks like this. This one we don't know. And then it has a mirror, which is let me see. Right. The mirror should be somehow looks like the Hodge diamond for the mirror. And then we can define the I functions by, so we have some cycles of this H3, and we can define this IK. be something like this, such that this I0 starts from, it is regular. And the maximum unipotent monodromy say that we hope this IK looks like log Q plus some regular term. So this property will be log Q, maybe I write it as I of Q of. So this means okay. So first we pick some bases here. So because this is we pick some bases here. We call it phi of. And the corresponding basis so because we have this Q and the Q to the alpha will corresponding some small Q to the alpha. So they are at the same direction at the origin point. And then so this basis determine this coordinate and determine uniquely this I of and by the property. And we write down the basis here. We call it the E alpha. Okay, so locally we have such a correspondence. Here, this is this neighborhood near the Q equal to 0, and this is a neighborhood near the small Q equal to 0. And they are related by the so-called mirror map. Then the mirror map is, so the classical mirror symmetry told us the mirror map is just given by this Q of is equal to this E to the I of Q over this I0 Q. So this is the you can change consider it as a change of coordinate, and this is just the classical mirror symmetry told us. And then we can see that we can just identify these two bases, these two vector space, this H2, H11, and here of X, and H21 of H, the mirror of X. And then here, this we can just identify the basis. So here the basis is, as I wrote, is phi of. So we can identify it as this Q of partial Q of. So it is equal to this Q bit Q of and E bit. Let me check. Right. So this is a relation between them. Okay, and then we by identifying this basis, we can define the Yukawa coupling. So we define this Y I J K, which is defined by 0 square times this E I E J and E K 0 3. So notice that this E I E J E K they are not flat bases on the Gromov-Witten side. They are just the basis on the B model side. But this correlator is defined by the A model, by the Gromov-Witten 3-point function. Okay, so the mirror symmetry, the first result of the mirror symmetry. So the mirror theorem, the consequence of the mirror theorem just say that this YIJK is global meromorphic function on this whole modular space. So in our case, in this talk I will mainly consider that this X is some computer intersection in toric variety. So in these cases, this YIGK will be given by some rational functions in some so QI, and this QI will relate to the parameter in the toric variety. So roughly speaking, we have something like this. We have this YIGK should be equal to the delta of some polynomial in Q. So this is kind of equivalent to the mirror symmetry statement. Of course, there's this polynomial we can compute it by using, for example, by using the Picard-Fox equation, which the Picard-Fox equation is the equation that this omega Q must satisfy. So here there's just some finite data. So I like to state the mirror sim in this way because this statement, in fact, I think it is kind of a specialization of the BCOV's Feynman rule. So let me now introduce the what we call the BCOV's BCOV's Feynman rule in my title. So BCOV's Feynman rule is a structure proposed by Boshevsky, Sarkoty, Ugru, and Bafa, and they say that for Calabi-Yau threefold, so you can consider something in the following form. So this is a Yukawa coupling, which is a 3-point function. We can define, for example, we can define this P G K for general genus. So we defined by 2 minus 2G. I0 is the period we already mentioned, and we have BK1. We can also define something like this. And of course, YIJK is just P0 IJK. So BCOV's Feynman rules say that we can consider something like the following. So we consider a graph sum, so we call this small FGK as a graph sum. So as a FPGK plus some lower order terms. And then these are just some, so you can define for order of this G. And for example, you can define the order by the 2G plus minus 2 plus n. And then this, you can see that this small FGK, so their rules say that this guy will be something which looks like delta 2G plus minus 2 plus n over some polynomial in Qi. So we can see that by their rule, then because these are just lower order terms. So suppose we compute these polynomial. So these are called ambiguity. So in mathematically, we just consider it as an initial condition. which are finite numbers. So suppose we compute this finite number of these invariants, and then we see that this PGK can be recursively compute just order by the order, right? Of course, the order will be related to genus, so we can compute this PGK from the genus 0 to higher genus recursively. So that's why this BCOV's Feynman rule is gives a very effective algorithm to compute these Gromov-Witten invariants. So so right now I will to give the precise statement of this definition of this lower order term. So to be precise, this FGK can be defined as a summation of some stable graph. So this gamma is a stable graph. For stable graph, we mean a stable dual graph. So let me just write an example. For example, when Gn equal to, so for genus 2 case, this stable graph will be, so the stable graph means that each component is stable. Means so a dual graph is something you have some vertex, you have some edges, you have some legs, because here n equal to 0, we have no legs. So then we can draw all the stable graphs for genus 2 with no marking. So this graph will be here. This is genus 2. It's 1, 1. It's 1. And you have something like this. This is, you have one edge, you have two edge, you have two edge. This another possibility is, let's see. You can have like this, and you can have three edge. Which looks like this. This is these are all the possibilities. So stable just means for each vertex, you must satisfy 2G minus 2 plus n larger than 0. Okay, and then we can define the contribution by the following. So the contribution is just the you have some edges. So in this case, we have you have vertex with some edge or leg. So these legs can be half edge, and you can have something like this. So at each vertex, we just put this correlator. And at each edge, we put something like this SIG. And at this leg, we just put something like. Okay, let me just give an explanation of this. So EI is just the ordinary EI when I is not 0, because EI is a basis. So we call EI as a base. I is from 1 to H is a basis of H2. We already identified the H2 and the mirror. So we identified them. So we can think EI is basis of H2. Of course, to be precise, we can consider it as this. So A is some foremost series in occur variable. And then, but we need to define E0. So E0, we consider it as this sidebar times phi 0. So phi 0 is just 1 in this h0 of x. So then by this rule we can, so for example, if you have like this graph, then the contribution will becomes, you have a bracket here with two wait, we don't have this graph in genus 2, so maybe let me change the graph. So for example, we have this graph. So we have bracket here. This is 1, 1. We have bracket here, which is 0, 3. So we put this half edge here. So we have two edges. So this two edge will give Sij tensor Sij. And then we will have you see, we will have for tensor, and we will have this bracket eat all these vectors, and we will get a generating function. This generating function is just the generating function we want. Okay, so here this Sij are the so-called propagators. Defined in BCOV's paper. So they defined by doing some Feynman integral and then take some holomorphic limit. But we hope to have a mathematical explanation of this, and this mathematical explanation will be useful when we consider the how to prove this Feynman rule in the A model. Okay, any questions? Okay, if there are no question, I will continue. So, first I want to say that this BCOV's Feynman rule, you can realize it as a, so it is some graph sum, but you can realize it as a sorry, I mentioned here. So this ki we can define by this or is I0. It can be also defined by in BCOV's paper as a holomorphic limit of some Feynman integral. Yeah. So we have some we have the propagators two types. One type is ki, the other type is Sij. Yeah, I want to say that this in BCOV's paper they use this notation Sij, Sis, which corresponding to our Sij, Si0, and S00. Okay, and then so I want to say that this Feynman rule can be realized as a integral representation. So we just write down some matrix we call propagator matrix, which looks like this. Depends on Z. These are some blocks. So this is 1 H. There is okay, there is a matrix H times H matrix, which we put the times as Ij here. I put the queer S star 0 here. here we put something we call S plus I0 ki. And here these two are determined. Oh, this one should be here. These two, we require this PZ satisfy this this sympathetic condition. So then this part can be determined by this condition. And we can also write down it as blocks as this. Let me see. Should be. Okay, and then let's see. Then we can define this quantization action as the following. This is the standard definition of the so-called geometric quantization. And here this quadratic form is determined by this big matrix. And you can see that you can by just computation see that this definition is equivalent to the graph sum. So here we just write down this f(x) as the generation functions. So we just write it as p g k x k. H bar record the genus information, and then you can see that this this quantization will just exactly give the graph sum you want. Okay, so this is the so-called the BCOV Feynman rule and its geometric quantization realization. And then I will return to the A model. So in the A model, we don't have such things, but we have something very similar.
Hi.
Hi.
Excuse me, so what's the meaning of Z in your package propagator PZ? What's the meaning of Z, small z in his PZ? Is just a formal variable to...
Yeah, good. So Z is a formal variable, so sorry. So here, okay, so right now you can just simply think Z is just a formal variable because, okay, maybe, yeah, I should say that. So I should say that right now we need this space to be sympathetic, but because we are using the A model space H2, it is not. I mean, we are considering this space. I should say we are considering H0 X. In the A model, so it is not sympathetic. Let's see, this is a vector space of V. So we define some space called this this is defined by Givental, called the very big infinite dimensional symplectic vector space, and we define this for Fg that's in this space. We define the pairing by the following. So this is a standard inner product. So this is just defined by. And then because we add some z here, we can see that this is symplectic. And for the above, so because we need to, okay, see here, I should write this as bracket. So here, in fact, we just consider some, I'll say some small space. We can consider this symplectic space as a subspace of the very big infinite dimensional space. So we consider something we call HB. This HB. So let me see where this matrix actually is acting on. So this matrix act on this B is spanned by let's write the Z0 E1 3 minus 1. Sorry, E alpha. So E is alpha is a dual basis of small e alpha. So we have basis here. We have E0 here. And we have this E alpha and the E alpha 0 here. So we just formally add some z here. So this formally z will not change the pairing, but will make it symplectic. And also this formal variable z will make this HB as a subspace of this infinite dimensional vector space. And okay, so in fact, Givental defined this the so-called Givental's quantization over this symplectic vector space, this infinite dimensional one. That is called his R matrix action, and that definition is different from this geometrical quantization defined over this HB. So, but roughly speaking, I want to say that the geometrical quantization defined here, so is so you can use some axiomatic property of the Gromov-Witten theory to prove that this quantization, maybe I should write it as PB hat, somehow equivalent to, it is equal but up to some constant also. So I will just, because time limited, there's too many details, but I will just roughly write this will equal to this Givental's quantization. And in Givental's quantization, because it is defined over this very big space, it is an infinite dimensional space. And then in Givental space, we can see that the Feynman rule will be much more complicated than what is in the B model. So for example, here we can see that here we only have the propagators Sij with the basis of EI and EJ. We never say some dual basis, like for example, here we put some E0, and then in right hand we put some E upper. We never see something like this, right? We only have, so all these guys lies in H2, or maybe I should say it lies in they are all the degree 2 class, so they are all degree 2 class. For example, this E alpha is just lies in the H2, and for the E0, although the phi 0 is degree 0, but this psi class you can think it is degree 2, so this is also degree 2. But of course, in Givental's quantization, we can have all the possibilities of degree. So we will have something like, as I mentioned, we have E0 here. This is lies in H0. I should say this is degree 0, and this can be degree 4. It has much more graphs, but we can prove that. So here these two quantizations are almost equal, just up to some correction terms. So that's why we consider this geometry quantization and the Givental's quantization, this language, because they will allow us to use Givental's quantization. So to summarize, I want to say is that the BCOV's Feynman rule will be equivalent to say that this guy has some polynomial, has polynomiality, and this p hat is it will naturally appear in Gromov-Witten theory, because that's why Givental introduced this. Okay, sorry, but this is just very beginning of this story, and okay, we still want to define this this P by using the A model. Okay, so what I want to say is that, so here P right now it is from the B model, and if you want to define it using I function, it is very complicated. But Givental, okay, Givental tell us something very important. So he say that we can consider some subspace L, which is equal to P. Zero. This is a subset of this E. This one. So here P, you can think it as some. Okay, this P is just I should say this Q is usually maybe we can write Q before P. This Q is something like T of Z. Okay, no, sorry, I will not use this notation. But anyway, it's a okay. It will looks like the so-called J function at this point T. Maybe I should write down the explicit formula. It will looks like Z plus T minus D plus something looks like this. This definition is exactly the same as this one. So it's just say that, so T is the variable, so TZ is a formal variable. It's a coordinate, so it is, you can write it as T0 plus T1 Z T2 Z square, and TK lies in the homology. TK is a harmonic class, and Z you can consider as it as a psi class, and then you can see that this definition of this J is equivalent to this definition. And Givental say that if you consider this subspace, it will be a Lagrangian cone over this symplectic vector space, and it will have the property that when you do derivative of this Lagrangian cone, you will still get the element in it. So okay, maybe I will just write down Givental's thought. Say that you use string equation plus delta equation plus topological recursion relation will deduce that L is Lagrangian cone, and to be more precise, L is equal to something we call the S matrix. The S matrix is also it will appear in the genus 0 Gromov-Witten theory. It is just consists of some genus 0 Gromov-Witten invariants acting on this vector space with only positive powers, with non-negative powers of Z. And this Lagrangian cone has the property that when you do derivatives, it will still lie in this cone. So by using this property, now, so first the mirror theorem has another statement. It's just say that this I function, if you write Z times I0 plus I half V half. So I alpha is just as defined above, and you can define because here we only define the here. Okay, let's see. So here we only define to up to I alpha. We can still define what we call I upper alpha and I0, which start from log Q square and log Q to 3. So we can define some we can define some I function here. So maybe I will just keep this. And given those results, just say that this I function lies in this Lagrangian cone, and then you can consider the derivative of this I, and roughly speaking, we can consider this matrix if you consider I as a column vector. And we consider this as a matrix, this one, this H. And we can consider some linear compositions of this guy. We pick some CIJK suitably. This is not hard because we know this H2 can generate this H4. And we can also have some linear composition of this guy. This is only one. So this linear combination will corresponding to some phi upper alpha. to be precise, in fact, it is correspond to E upper. And we can see that all the elements of this M will lie in the Lagrangian cone, and then by this property, we will see that this M must have, and we can pick these bases suitably to make this sympathetic. So we can see that this M will, you can write it in terms of this S1 acting on some PZ. So maybe here I will just one more, because there's still some change of basis. So we can write this guy. So this will start from 1, and this one is just something like this. This is just the standard Birkhoff factorization, and this is a change of basis from this phi to this phi to this EF, from A model to B model. You can check this because this is start from I0. Okay. And then, so we claim that this PZ appears in this Birkhoff factorization is just exactly the propagators defined in BCOV's Feynman rule. And then we can see that this, okay, so furthermore, we can see that this BCOV's Feynman rule, so right now it is something like, if we denote the common field theory of this X, Gromov-Witten theory of X by omega X. So as we mentioned, this BCOV Feynman rule just says that this theory has polynomiality. And okay, so once we claim this guy is just the same as this P, so how we can prove this property? So the idea is the following. So so now we consider this Gromov-Witten theory of X, and for X is computer intersection in toric variety, as I mentioned. So the idea is that we consider a much bigger space contain this X we call the mixed spin P field theory. So we it is very complicated, but the idea is simple. So we consider some bigger space, very big theory. It contains this X as part of it. So roughly speaking, if we consider this Y has some torus action on it, so maybe we use G to denote this torus action. Then very roughly speaking, this fixed point of Y, of course, it does not contain X, but in the virtual cycle level, it is. So we just very roughly write that this big theory will contain X as part of it, and some other part. And this geometry of this big theory will still have this polynomiality. Okay, and also there's a very important philosophy in Givental theory say that when you do localization, this localization you can realize it as an R matrix action. This is the quantization of R matrix action. So roughly speaking, so this means that this localization procedure will tell us this big theory will be equal to some very big R matrix action acting on this Gromov-Witten theory of X. The co-FT we will just write it as omic x plus some other theory. Okay, so this theory will have the polynomiality. And this R is complicated, but the main observation is that this R, we want to prove that it will contain this P, this propagator as part of it. So we want to say that this R is equal to let's see what it should be on the right hand or left hand side. It should be okay. So usually we use this R inverse. It will be by seeing something we call this. There will be this propagator, and we just put 1 here. This component corresponding to the X component and all the other component. Acting on some big matrix, we call it G. Okay, and then we claim that this G also have the polynomiality. So then we prove this this P acting on this omic X has the polynomiality by proving the G and the entries of G has polynomiality, and this R acting on this whole series has the property. And to prove this factorization, in fact, it is essentially related to the above this factorization we mentioned. So we should say that this M is equal to this guy. And for the R matrix defined by the localization, it is also from something we call, so this R, we can prove that originally it is from I should say it is from the big S matrix. This is the total space S matrix, factors by some blocks X and some other part, this other part, acting on this this R. Okay, so we can, there's also some side here. So we can see that this this block part of this factorization is just matched with this factorization. So to prove this G has the polynomiality, in fact, our idea is just to prove this the equation that this Sy satisfy and this S minus S inverse this of Sx satisfies. We'll have some recursive way to using this two matrix to compute this G, and that will preserve the polynomiality. And by using this tool, we prove that this A model equivalent of the BCOV rule. That's the main purpose of this talk. Okay, so I think I will stop here. Any questions?
Okay, thank you for your talk. Any questions? Okay, probably could I ask, could you please recall the main idea is that this BCOV Feynman rules is a conjecture from physics, yeah?
Yeah,
And,
yes.
And you are proving it using this geometrical quantization, yeah?
Yeah, right.
And it works in any case, yeah? It's applicable.
Roughly, the idea right now should work just for the complete intersection in toric variety, because for the big master space, the big space, we can only construct it by using some structure that we need for like computer intersection in toric variety. Of course, in for original BCOV Feynman rule, it says that this is graph sum is you have some polynomial structure, right? As I mentioned, this is polynomial, but this polynomial, in fact, also realize that I think it needs this Calabi-Yau threefold should be some like hypersurface or computer intersection in toric variety, because I think even for the original mirror theorem, it will require this condition. If not, so how you can say what is the polynomial in Q? Because if it is just a Calabi-Yau threefold, you have no idea what the modular space is, and you don't know any structure like this. Yeah, so right now we just consider the computer intersection in toric variety.
Okay, thank you. Any other questions? Probably people in Zoom. Okay, if not, let's send Shuai go for the talk.
Okay, thank you.
Yeah, thank you very much. And could you please send me your slides, your